Hello, class. We're back. Now, while I was waiting for this computer to, I guess it's download or whatever it's doing, I had a few minutes, and I think I'll hold off on PSI and 2.31 feet. It's actually a very big, that in itself is a pretty good sized class. Let's hold off on that. There's some smaller things I'd like to get to that's actually, I think it's in the order that you find on that formula page. So, we did the square inches and the square feet, and the test pressure and the working pressure. Okay, the next thing that you'll find is triangles. Now, the perimeter of a triangle equals the three sides added together. Okay? So you just add three sides. And as you all know, triangle, that's all it's got is three sides. So if we get a triangle like this, we got 8 and 4 equals 12 inches for the perimeter, right? So the perimeter here is 12. Just add up to 3. That's easy. Now, what's a little more difficult is, it's actually just a little bit more work, is the area of a triangle. Now, let's take a look at that. Area of a triangle equals length times altitude divided by 2. Okay, now if you never heard that formula, it's like, what the hell, what's that? Okay, that's easy. Let's take a triangle. It's like a pyramid. All right, now I want to find the area of this triangle. Okay, we'll say that this is 14 inches, right? And from here to here is 8 inches. Like that. That's the altitude. They call it the altitude. You call it the height. To me, the height is easier, right? Oh, actually, they do call it. I'm sorry, I've heard it called altitude. Okay, base times the height. So it's the length times the height, right? Divided by 2. So let's see what that comes out to. So you get 8 times 14 divided by 2, right? Triangle is always divided by 2. And that's come up to 56, right? So this equals 56 square inches if we're doing inches. Okay? All right. That's it. Okay, so when you do the area of a triangle, again, it's probably nothing you're going to use on the outside, but never know. The state might be looking for it. So let's take an example that you can prove how a triangle, you change that to height. Sorry about the altitude. Heard it call that, but not in this one. Okay. So how can we prove that the area of a triangle is half of something else? Let's take that same problem. We'll say that this is 12 inches long, like this, and 8 inches high. All right, now that's easy. Length times width, we all know that. Length times width equals area. No big secret. Okay, so 12 times 8 is, should know how to do this. (96 square inches). Okay, pretty simple. 8 times 12, 96. All right, now let's cut this diagonally in half like this here. Just like a piece of paper, you're going to fold it over. All right, this is still 12, but I got rid of this half over here, right? So half of that rectangle is gone. Not there anymore. That's where the 2 comes in. So length times width. Now we really don't have length times width anymore. That's why they call it the height. So in this case, it'd be 12 times 8. This would be the length times the height. Equals divided by 2, right? See that? There it is, divided by 2. So it's 8 times 12, 96 divided by 2. Okay? And that's going to be 45 and a half. Oops. No. 90, 48. Yep. Okay, so this would be 48 square inches. If it was a rectangle, if we made it back like it was, it'd double. So that's why you got to divide. When you have a triangle, don't forget it. It's easy, but if you forget this, and the state could be sneaky, and what they could do is give you an answer that would be this answer, like a rectangle, and you'd spot, oh, that's the right answer. No, it's not. They're trying to fool you. Divided by 2. Okay, and it doesn't matter the shape of a triangle. This one, it worked. All right, I picked this triangle because it works. If you got a triangle that looks like the one we were using before, you would have to add like this here. Not so easy. All right, but this one is obvious because you have the same. You would have to actually just double this. In other words, make a copy of this and just kind of flip it over. That's where the 2 comes in. All right, so I'm not going to spend any more time on triangles. It's a form that you should know. But beyond that, I don't think you're going to use it. Except for a test. Now, the area of a circle, I think I've done it with one of you. This is a combined class, but I think I've done this. If I haven't done it with one of the groups, I'm going to do it now. And if I did, just bear with me. This doesn't hurt getting a review on this one, because this looks like a question you might get. Let's say you want to find the area of a circle. Equals. This is the formula I had as a kid. That's okay. If that's the one that's burned into your brain, if they beat that into your head when you were a kid, go with it. All right, you won't forget it. Now remember, all these formulas I'm going over now, there is no handout sheet for this for your test. You either know these or you're up the creek. Okay, so if you like that formula, let's work one out. So let's say we have a circle. And that circle, not bad, looks pretty round. Okay, let's say the diameter is 12 inches. Right, that's right through the middle of the circle. Something like that. Shaky arrow. All right, we'll do with that. It'll be okay. 12-inch diameter. Okay, what's the radius of this one? The radius is going to be half of that. Remember, R equals 1/2 D, or D equals 2R. All right, so the radius is going to be 6. So the formula will be pi 314 Don't forget this. Times the radius, 6, squared. All right, so it's 3.14 times 36. Okay. Now, I know I can't talk to you right now, but if you get a question on any of this, please make a note of it, and we'll cover it in when we go live. All right, so what is this here going to be? 3.14 times 36. Times 36. All right. You know what? Just to save time, I got a calculator here. So we got 3.14 times 36 equals 113.04. Okay, square inches. That's it. Now, if you want to know if you screwed up, you could multiply as if this was a square. 12 times 12, 144. All right, a circle is a lot less than a square because you got the four corners cut off. So if you're coming up with something more than 144, or way lower, we'll say 80, you know you screwed up. Okay, it's going to be about 75% of the circle will be about 75% of the square. All right. If you get any questions, hang on to them. That's the answer for a 12-inch circle. All right, so that's pi r squared. A good formula, easy to use. Now, because you're using calculators, it makes a difference. Years ago, I would have picked the one I'm going to show you in a second. But with the calculator, as you can see how it was pretty easy to do. But this one here that I'm going to show you, I think is easier. Now let's do what I said, make a square out of this. I'm going to come right across the top and down like this. Shaky on that one. Okay, so you have, let's say it's a piece of paper and you're a kid cutting this out. You got those 4 extra pieces. So that's where you go from that 113 up to 144, right? If you divide the difference by 4, you'd find out how many square inches are on each of these here. It's 5 or 10, whatever it is. Right, now there is a formula, a very clever formula that I didn't know until after I had my license. Maybe I wasn't paying attention, but I don't think we covered it because it was always pi r squared. But I think it was after I might have even already been teaching when I came across this formula. Right, you have a circle equals the diameter squared, right, times 0.7854. Right, now on the formula sheet, I believe that's what it says anyway. Or if it's pi, I have just my own notes here. I don't have the formula sheet in front of me. And but I believe that's the one that the book gave you. Or the pi r square. I'm not sure. Maybe they gave you both. But this is the one that I would pick. Remember this one here. And here's the reason. This diameter, right, is 12 squared. This is like what they call a constant. It never changes. It's kind of like pi. It's one of those things that somebody really smart figured out probably thousands of years ago. All right. What this means, before I go any further with this, 0.7854 equals 78.54%. Okay? So what it means is you've got a square and you want a circle cut out of it. You cut it out. The circle is 78.5%, well, 0.54% of the square. Okay? So let's do this. 144 times 0.7854. Okay. Now, I could do longhand, but you know, it's gonna take a while. So let's do this. Here it is. Now that's 113.04. So let's see if I use this formula. Let's see how close it comes to 113. So we got 144 times 0.78. Oops, do that again. 144 times 0.7854 equals, okay, 113.09. Slight difference, okay, but not enough to be a problem. Now there's an example of an answer being plenty close. The two of them are going to be almost exactly on the money, and the one that you'd get on a test wouldn't even been anywhere near as close as that. It might be just 113.1, we'll say. Okay, so this formula comes out to the same thing. Instead of 04, it's 09, which is almost nothing. Okay, and that's in square inches. Well, what I like about this formula is that it actually kind of explains what this constant is. It's a percent. 78.5%, which is exactly what we did to solve it. We multiplied 144 times 78%, or what is 78% of 144? Okay, so the circle is roughly a quarter smaller than the square. That's it. That's the whole thing. All right, let's see how we're doing for, now we're fine. Okay, we did the area of a circle. All right, now we're going to get to the what I had up on the board before. So we had one. Okay, just a brief refresher. This piece of plastic here, we'll say we had a gauge at the bottom, the cap at the bottom, poured water on the top, and we watched the gauge go up, right? Quarter pound, half pound, and it got to 1 pound when I came up. There's 2 feet, about right there, and about somewhere around here would be 2.31 feet, and that gauge would be reading 1 pound. Now, one thing I didn't mention before was that the diameter of the pipe doesn't matter. It could be a pencil because it's measured in pounds per square inch. So in other words, the gauge is reading how much, let's say we have a square inch right here. We'll make a pipe out of a square inch, square piece of pipe, okay? Like that. So this is actually a little more than 1 inch, but we'll say it's 1 inch. And it's square. And the gauge is hooked into the bottom. You go up 2.31, and the weight would be 1 pound per square inch. Okay, so it's bearing down just on that 1 square inch. Now, if it's a pencil, same thing, right? It's still a height. We don't care about how wide it is. So this could be something like a pencil width wide, or it could be something, a water tank 100 feet across, like in the city. Doesn't matter. It's the height that makes the change in the pressure. Okay, we're not worried about that, but I just want to make sure you understand it. The diameter of the container or the pipe or whatever it is that's up in the air is not a concern. All right, it's the height only. All right, now the reverse of this is, let's say we have 1 foot. Let's say we have, here's a ruler right here. All right, and the pipe is 1 foot high. Okay, and I put the gauge in the bottom. Now what do we got? Well, obviously it's not 2.31 anymore. So 1 foot equals 0.434 psi. Okay. So, when you have an underground job and you have to test it, and you have we'll say a 2-inch piece of PVC or no hub or whatever it is. It's going to be your standpipe, right? You get a pipe up in the air 10 feet. Maybe you put a threaded rod or something, or rebar or whatever to hold it straight, hold it in place. And your boss has you fill up all the underground piping, cap it all off, check it all out, make sure you got no leaks. The inspector could ask you to let me see the water come out the top. You have to, hit it with the hose wherever you have the hose hooked up, and he can see the water coming out. So he knows that you got that pipe filled with water. So what kind of pressure you got on that piping? Okay, from where the bottom of that 10-foot piece of pipe is, you got a 10-foot, what they call head of water. Now, a head of water 10 feet high would be this, right? There's 1 foot, it's 0.434. So 10 feet of water would be this, right? Would be 10 times this, which is easy. It would be 4.34 psi. So for those of you who have been doing this for several years, especially you tier 2 guys, or anybody who hasn't, it's been working on the books, on the however you've been working, you've done these jobs. Maybe you never gave this a thought, but that's how much pressure you're putting on your system. So 0.434 isn't a whole lot of pressure, but it's a bit. Now, I'm just remembering a job, it was at the time, it was like horrifying for me. I was at a job in up towards Boston back in the early 80s, just before I started teaching. And I think I mentioned the story to you guys. I had, I guess it was an inflatable in the water closet elbow. And I had something, I think I had something over it. Maybe I had no, I don't think I had wood holding it down. Maybe I didn't have anything. That's what it sounds like. Anyway, it's probably when I was still trusting these inflatables. And I'm standing there talking to the inspector. Now, this was in like a basement. And or the first level, it was kind of like not a raised ranch, but it had a basement on this lower level, but it had 2 more floors above. And we were just standing there shooting the breeze for a couple minutes. All of a sudden, the thing popped out, and it wasn't like it went. It was enough so that we jumped back, and the water came out like some kind of waterfall thing. It went up in the air several feet, and I was like, oh crap! But he didn't hold it against me. Everything else was tight. He was done, but I learned a lesson. So what happened? Now, when you guys test out your underground piping, which if you haven't done it, you will. Trust me. You all will be doing this sooner or later. You'll be testing out the underground piping. Any inspector who lets you slide on this is making a mistake, because although we're not too concerned with a few drops of water dripping into the ground, let's say you had something and it was up PVC, and you know how PVC sometimes spits the pipe out. We'll say it's right on the edge. If you weren't careful, it could actually just pull apart. You might catch it if you tested it with water. You might be able to see it because it probably would be leaking. But in any case, it's always good to test the pipe with 10 feet of water. Okay, so let's say you try more than that. So what happened here with this job I'm talking about? Well, I had maybe 10, 20, plus the attic in that. So I had about 30 feet on top of this, the job that I was doing. So it looked like 3 times, instead of 1, it was 3. So 3 times this is 12 and change. It's almost, 12. So I got 13 pounds per square inch. All right. Yeah. Well, now think about this. How many square inches in a 3-inch elbow, or 3-inch anything? Okay. Well, let's figure that out. Keep that in mind. We're going to put that aside. Let's make it 13. All right. So we have a 3-inch pipe, right? And I want to know how many square inches that 3-inch pipe is. I think it's 7. But anyway, let's find out. So I'm going to use that formula I told you. Area equals diameter square times. You can do times like this, or you can just put an X, whatever one works. Diameter squared times 0.7854. So this is going to be 3 times 3. So we got 9, right? Diameter times 0.7854. So what's that going to look like? Well, let's check it out. We're going to have 9 times 0.7854 equals 7. Yeah, I did remember it. 7.06. 7's fine. Now, remember what I said. That's pounds per square inch, right? So every little inch is 13 pounds. But I got 7 inches in my 3-inch pipe. So what do we got? Not PSI, 91 pounds pushing up. I think you'll all agree that would you really want to trust an inflatable? I know they tell you to fill them up to what, some crazy like 5 or 10, 8 pounds or something stupid. And I'm sure that you guys all fill them up a hell of a lot more than that. But even when you fill them up a lot, that plastic is slick and it can blow right out. So 91 pounds with that's with a 30-foot head on it. I wouldn't trust the inflatable. And I'm sure some of you guys have experienced this where you put the plug in and either your boss or an older co-worker will tell you not a good idea, or you learn the hard way like I did. So what I would suggest you do is when you have a water closet, especially when you got, say, 20 feet above, even 10, 15 feet, do yourself a favor. If that elbow is flush with the floor or close to the floor, put a piece of ferrin or some other piece of scrap wood, even if you got to put 2 little pieces of scrap on the side of it to clear the top, and use some like deck screws. Don't have anything like that around? No problem. Get your toolbox or some other heavy box or whatever you got, something with some, some weight to it, and put it on the elbow itself, right? If the elbow is up in the air, be careful. You don't want to bend anything too much. But I've done that for years, and after that happened to me, I never had another one blow out. Now, looking at this here, that's more weight than I would have guessed it was. Even a heavy toolbox is probably 40 pounds maybe, but it's always been enough to hold it back. So for those of you who haven't experienced it, don't be careless. If you got you're capping a 3-inch pipe in particular on a lower level, put something on it. Put something good on it, on top of it. Now, if it's like a gym cap, the ones with the hard rubber with the hose clamp, that might be good enough. But for water closet, it's usually inflatable because you got an elbow there. There's not much else that's going to work. Okay, enough of that. Let's see how we're doing. Okay, we got a little more time. Also, if anybody's got a good story to tell, you guys, it's always fun once in a while to tell a story, especially something that applies to people like that. A story where something blew out on you, your boss, or whatever, or you heard about one, and story to be true. Pass it along, right? Somebody might get something out of it. Okay, we only have a couple minutes left, so what? Going back to where I started here, with the pounds per square inch and feet. Well, actually, that was an example of it. Now, the book gets into stuff other than, now that's like actually something practical, at least it was for me when I was out working with the tools. And the book gets into some numbers that are a whole lot higher than that. We'll say you have a 50-story building. How big is a story? Okay, a story typically is 10 feet. I don't know if that's the engineering standard or architectural standard, I'm not sure. But our book says that a branch interval a story. Let me write this first. And I think I said this to one group. So when you hear the term a branch interval, okay, in plumbing, the story is a branch interval. So what would that be? Kind of like a branch on a tree, right? Here it is here. This would be 8 feet minimum. Now we all know that the height of a ceiling in an average house is maybe a little less than 8 feet, but not much. But then you got to add in what? A 2 by 10, some ferrin, sheetrock, flooring, subfloor. So you're looking at over a foot thickness from the ceiling to the floor above. So you're looking at probably 10 feet, 9 feet, 9 and change. But the commercial buildings, I believe it's 10 feet. Anyway, plan on 10 feet. But our code says a branch interval cannot be less than 8 feet. But now you know what a branch interval is. And a branch interval would be kind of like this. It would be something with a couple of water closets, a commercial building, or it could be just a regular water closet right here, like a regular residential. But I'm showing a commercial buildings. That way I can use these branches. All right. And toilets in a line like this here are what they call a battery, right? Where you get 2 or more fixtures on a similar fixtures on the same elevation. So this is a branch interval, a story. So let's go back to what I started to say. 50-story building is how many feet high? Well, that was pretty easy. That'd be 500 feet. Okay? 500 branch intervals. All right, so a 50-story building is 500 feet. Give you an idea how high that is. I think the buildings, Hancock Building, some of the bigger buildings in Boston would be around 500 feet. And the Washington Monument in Washington is 555 feet, if my memory's right. So that's pretty high up. And so what would the pressure be at the bottom to pump water up to the top floor of a building like the bigger ones in Boston? So how do we figure that out? Remember that 0.434 equals 1 foot, right? 0.434 psi goes 1 foot. Now we got 500 feet. So what we have is 500 times 0.434. Okay? And I think that's going to be 217, but let's check. So if we have 500 times 0.434 equals 217. All right, that's right. So what's that mean? It means if you're standing at the bottom and you want to pump the water up, let's say you just finished the plumbing and you're going to test it. Well, first of all, I never worked in big buildings like this, but I do know from actually one of my students who worked on the World Trade Towers, this going back over 20 years, when I worked down at Rogers High in Newport teaching night school. And he actually worked there in the towers. This is before they fell. I left that school back in the late 90s. And he was telling us how they tested it. Everything was in 10 stories. All right, they pumped everything up 10 feet or everything went down. So it was like 12, because it was 120 stories, if my memory's right. So it was like 12 buildings stacked up. You didn't have like everything falling at 1,200 feet. It would be like 12 10-story buildings. Okay, but let's say we had a 50-story building and we're not considering any of that. We just want to pump water from here to the top floor to fill the system, the drainage system. First of all, they'd probably use air up there anyway, but let's say we want to get water up there. It would take 217 pounds pressure just to get the water up to that floor, right? With no pressure on it, with nothing. So if we started pumping, we'll say at 3 or 4 feet high, we'll say it was 500 feet. So at this height, you would have zero pressure. In other words, the water would be just sitting there, ready to come out of the pipe. And then you would have to add another, 40 or 50 pounds. So it would be 267? 257, 267, to get it up to a pressure that would be acceptable for an apartment on the top, like a penthouse up on the top. So you have to have some pretty big pumps. I think a lot of these buildings have tanks on the roof. If you have seen a disaster movie, I can think of one where they had the big tanks on the roof that they pumped up, and then the tanks fed down from there. So anyway, that's how we do it. 0.434 times the height in feet. Okay, we're going to run out of time. We already did. So I'm going to cut this off, and I will see you back in class.